Now that we have seen a review of complex numbers, let's dive in and take a look at polynomials that have complex coefficients, and we'll look for complex zeros. Remember that all real numbers are also complex numbers. So, the fundamental theorem of algebra states that if you have a degree of 1 or more on your polynomial, then you have at least one complex zero. Now, maybe the best thing to say is that there is a corollary from that, a statement that follows directly from that rule. The corollary is simply that if you have a polynomial that has a degree 1 or more, then it will have n complex zeros if you count multiplicity. So let's take a look at x squared minus 4x plus 29. So if we solve this, x squared minus 4x plus 29 equals 0, we'll use the quadratic formula. We have negative 4 plus or minus the square root of negative 4 quantity squared minus 4 times 1 times 29. And that is all over 2 times 1. So this gives us 4 plus or minus the square root of 16 minus 116. That's all over 2. So this is 4 plus or minus the square root of negative 100 all over 2. That's 4 plus or minus, now the square root of 100 is 10, and the I will be present because of the negative underneath the radical. So now that means that we have 4 over 2 plus or minus 10 over 2i. Remember that whenever we write complex numbers, we write them in standard form. So 2 plus or minus 5i. So notice that we have two zeros, 2 plus 5i and 2 minus 5i. The degree of our polynomial was 2, and we have two complex zeros. Now, moreover, notice that the zeros that we obtained are complex conjugates. If we have a polynomial function with real coefficients, then if we have a complex zero of a function, then the complex conjugate will also be a zero of that same function. So here we are supposed to build a polynomial function whose coefficients are real numbers. So we have a degree of 4. Now also we have zeros listed. So our zeros are 5, negative 3, 1 plus 2i. But this has a degree of 4, and we have real coefficients, so therefore 1 minus 2i must also be a 0 because it's the complex conjugate. Notice we have a degree of 4. How many complex zeros do we have? 4. So the remaining 0 was 1 minus 2i. Now we have a degree of 4, and our zeros are 5 with a multiplicity of 2. Then we have 2 minus 3i. Well, we have real numbered coefficients, so 2 plus 3i would also be a 0. We have a degree of 4, so let's add up our zeros, or not add them up, but add up how many we have. So we have 5, but we have it twice, so 1, 2, 3, 4. If we count multiplicity, we should always add up to the degree. So the remaining 0 was 2 plus 3i. So here we have been given a 0 of a polynomial function. And notice it has real zeros. So we automatically know that 1 plus 4i is also going to be another 0. How will we find the rest of the zeros? Well, we'll take a cue from what we had been doing previously, and let's go ahead and do synthetic division. So we have 1 minus 4i is a 0. Let's go ahead and look at doing synthetic division. So if I bring down the 4, now let's multiply. 1 minus 4i times 4 will be 4 minus 16i. If we add, we get negative 12 minus 16i. Now let's multiply 1 minus 4i times negative 12 minus 16i. So 1 minus 4i times negative 12 minus 16i. If we FOIL, we get negative 12. Outside would be negative 16i. Inside would be 48i. And lastly, we would get plus 64i squared. So this means that we have negative 12 plus 32i minus 64. So negative 76 plus 32i. So that gives us negative 76 plus 32i. If we add, we get 9 plus 32i. Now let's multiply again. 1 minus 4i times 9 plus 32i. If we FOIL, we obtain 9 plus 32i minus 36i minus 128i squared. So this gives us 9 minus 4i plus 128. So 137 minus 4i. So we have 137 minus 4i. If we add, we get negative 1 minus 4i. So now we should have a remainder of 0. So let's multiply 1 minus 4i times negative 1 minus 4i. 1 minus 4i times negative 1 minus 4i. That's going to be negative 1 minus 4i plus 4i plus 16i squared. So that becomes negative 1 minus 16, so negative 17. So we get negative 17. Add those, we get our remainder of 0. Now it seems really weird, but these are the coefficients of the next polynomial. So we can take those, the 4, negative 12 minus 16i, the 9 plus 32i, and the negative 1 minus 4i as the coefficients of our cubic. And we will now use 1 plus 4i as our 0 that we're going to use in our synthetic division. So let's bring down the 4. And this should be much easier now. Bring down the 4. 1 plus 4i is 4 plus 16i. This gives us negative 8. Multiply 1 plus 4i times negative 8, and we get negative 8 minus 32i. That gives us 1. 1 plus 4i times 1 is 1 plus 4i, which gives us a remainder of 0, like we had suspected. So now we have our quadratic equation. So 4x squared minus 8x plus 1 equals 0. Let's solve that. If we use quadratic formula, we get negative negative 8 plus or minus the square of negative 8 is square root of the square of negative 8 minus 4 times 1 all over 2 times 4. So we obtain 8 plus or minus the square root of 48 all over 8. So that gives us 8 plus or minus. Now 48 is 4 square roots of 3. And so we can factor out a 4. And so we get 2 plus or minus the square root of 3 over 2. So the remaining zeros, or x equals 1 plus 4i, and then 2 plus or minus the square root of 3 all over 2. So you'll notice we have 1, and then 2 plus the square root of 3 over 2, and 2 minus the square root of 3 over 2. There were 3 zeros. And if we go back, we were given a 0. So that's 4 zeros, and we have a fourth degree polynomial. So here we want to find the zeros of this polynomial function, and we want to write it in factored form. So let's start by finding the potential rational zeros. So our potential rational zeros, we start by naming our leading coefficient, which is a sub 5, and our constant. Now we need our factors of each. So these will be our q's, and these will be our p's. So our q's will be plus or minus 1, plus or minus 2, plus or minus 4. Our p's will be plus or minus 1, plus or minus 2, plus or minus 42, plus or minus 81. So our p's over our q's are our potential rational zeros, and we'll take all of these divide by 1, all these divide by 2, all these divide by 4. So we have plus or minus 1, plus or minus 2, plus or minus 42, plus or minus 81. Now we'll divide everything by 2. Plus or minus 1/2. Plus or minus 2 over 2 is already done. Plus or minus 21. And then plus or minus 81/2. Now let's take and divide everything by 4. So plus or minus 1/4. 2/4 we've already said with 1/2. And then plus or minus 42/4 would be plus or minus 21/2. And then plus or minus 81/4. So now what we can do is we can start by, with synthetic division, eliminating. So let's start with 1. Hopefully it works. So we'll put in our coefficients for negative 36, always being careful to make sure that no terms are missing. So bring down the 4, multiply, add, multiply, and we get a 0. So 1 was a 0 once, maybe it's a 0 again. We always check multiplicity. But this time, we don't check in the original, we check in the depressed polynomial. So we'll try 1 in for negative 32, 109, negative 163, 82. Bring down the 4. Multiply. Now if we add, we get negative 28. Multiply. That gives us 81. 1 times 81 is 81. And then that gives us negative 82. And it is a 0 again. Now, if it's a 0 twice, it might be a 0 a third time. So let's try this. And again, we're going to focus on the depressed polynomial. So we have 4, negative 28, 81, negative 82. So we have 4. 1 times 4 is 4, negative 24 when we add. This will give us 57, and it won't work, because 57 minus 82 is negative 25, which is not 0. So we'll go back to this, and we will now try the next number in our list. So let's try negative 1. Bring down the 4. It gives us negative 32, which gives us positive 32, and 81 plus 32 is 113. And that's definitely not going to be 0. That's going to give us negative 195. So that doesn't work either. So let's now check. Let's see what's the next number in our list. Positive 2. So we'll try the same depressed polynomial, 4, negative 28, 81, negative 82. Bring down the 4. That gives us 8 when we multiply. That's negative 20. This will be negative 40, and that gives us 41, which when we multiply by 2 gives us positive 82, which yields 0. So now we have a quadratic. So we have 4x squared minus 20x plus 41. So let's solve that equal to 0. X equals negative 20 plus or minus the square root of the square of negative 20 minus 4 times a times c. And that's all over 2 times 4. So this gives us 20 plus or minus the square root of 400 minus 656. And that's all over 8. So this gives us 20 plus or minus the square root of negative 256. That's all over 8. But 256 is a perfect square. So we have 20 plus or minus 16i over 8. So that's 28 plus or minus 16/8 I. And so that is equal to 28 reduces to 5/2 plus or minus then 2i. So let's take inventory of all of the zeros we found up to this point. We have x equals 1, and that was multiplicity 2. Then we obtained 2, and then we had 5/2 plus or minus 2i. Let's count them. 1 we had twice, so that's 1, 2, 3, 4, 5. And this was a fifth degree polynomial, so we indeed get 5 solutions that are complex if we count multiplicity. But now, what we need to do, now we're supposed to write this in our polynomial in factored form. So, each one of our zeros corresponds to a factor. So we have 1 multiplicity 2. That will be a factor of x minus 1, and that will get squared. Then we have 2, so that'll be x minus 2. Then we have 5 halves plus 2i. That will be x minus 5 halves minus 2i, because we'll have to distribute the negative. And then 5 halves minus 2i will be x minus that, will be x minus 5 halves plus 2i. So f of x will equal the product of those factors, x minus 1, quantity squared, x minus 2, x minus 5 halves minus 2i, and then x minus 5 halves plus 2i. Now, our leading coefficient of our original polynomial was 4. If we multiply this out now, we would have x squared times x times x times x. That's the leading coefficient of 1. So let's just multiply everything by 4. It will still have the same zeros, but the leading coefficient will now be 4 as desired.